In this video, I will discuss the kinetics and sizes of step growth polymers, both of which challenged me to think more critically about the subject. It helped me to look at the equations and think about probability, algebraic limits, and the type of reactivity in these polymerizations. So, in our discussion, we start off simple enough, where dA dt is in kind of a standard rate form, although we made it negative because A is actually being consumed in this reaction. Now, the first simplifying assumption we can make is that the concentration of A equals the concentration of B, because there would be no use in setting up a reaction where they were not equal. That would just leave stuff in the flask by default. But when we replace A and B with M, we get equation 1. The next piece of the puzzle for me to figure out in getting to the standard integrated rate equation was the conversion equation. So when I first looked at this equation, equation 2, I didn't know what P was, and I didn't know how they got to this equation, right? Now, P is just the conversion, and that's the number of reacted monomer divided by the number of initial monomer. Now, after some thinking, I realized we could rewrite this was just a rewritten version of the monomer equation. We have the concentration of monomer currently in the flask equals the initial monomer minus the reacted monomer, right? And then if we just distribute m naught, then we'll get the equation that's up here, right? Where this is in this form. Now, we can assume that the number and the concentration are the same because the volume should be constant over time. Next, to get the integrated rate equation, we'll have to rearrange equation 1. And that will yield this equation here, right? dm over m squared equals kdt. Once we integrate that, we'll get this relatively simple equation, and we can plug in equation 2 into that, the conversion equation, and we get this. Now, at first, I did some head scratching because I was wondering how P could be in the bottom of this equation, but once you break down the algebra, it makes sense. So, P is going to approach 1 all the time, and as it approaches 1, this becomes very, very small, which makes this whole term become very, very large. So even though P is in the bottom of this ratio, there is still a proportionality of time and conversion, where we have a higher conversion as time persists. I also had difficulty understanding the polymer size and dispersity in step growth polymerizations. Here, even though I don't like this notation, M refers to the polymer. So the degree of polymerization of a single chain is simply the polymer mass divided by the molecular weight of the monomer. Now, to get an average degree of polymerization, the equation is 1 over 1 minus conversion. So a higher conversion results in a higher degree of polymerization, if that makes sense. But due to the form of this equation, the curve ends up looking like this. So why is that? And for this, I had to think about how number average size involves picking any random chain. The low conversion region has low molecular weight because only oligomers dominate. There are still free monomers reacting with each other. However, all the monomers and chains are reactive. So as we approach very high conversions, the large chains can still react with each other, and they're the only entities left. So when we get to these high conversions, these large chains cause the degree of polymerization to rise extremely quickly because there are still long chains that combine with each other and double in size. Now, considering the weight average molecular weight, I harken back to the principle where dPW factors in the size of polymers. If I grab randomly in the flask, I have a disproportionately higher chance of grabbing a large chain than a smaller one. Because of that, 1 plus P appears in the top of the equation. Higher conversions mean bigger chain sizes. Bigger chain sizes are more easily picked than smaller ones. So both equations, the weight average degree of polymerization and the number average polymerization, approach infinity, but the weight average molecular degree of polymerization approaches infinity faster because of this principle. So when we calculate the PDI and the 1 minus p terms cancel, we are left with 1 plus p, such that the PDI can never exceed 2. This also makes sense because the chains are always reacting with each other and with monomers. That way, few chains will end up disproportionately bigger or smaller than the other chains.